So, welcome back friends. Okay, we are working on and studying the canonical quantization of a single real scalar field essentially. So, again just to revise that we started in the relativistic case, what we do is we start with the Klein Gordon equations of motion and then solve that Klein Gordon equation of motion in terms of this wave functions essentially and study the wave functions. But here what we do is we start with a classical field, derive the conjugate momenta. Okay, so it is slightly different and then uh, impose actually upgrade them. Okay, let me put it some sort of way. I do not know if it makes sense to say these things, to say it we upgrade them to linear quantum operators and then both phi and then impose quantization conditions in terms of this equal time canonical quantizations conditions. And then we said that we, because these are dynamical operators, collection of dynamical operators, then you can do a Fourier transform uh, of this in the momentum space and then solving for those momentum space solutions, we ended up having a description in terms of simple harmonic oscillators, because you see that okay, this is already covered in the last 2-3 lectures essentially. And so what we have finally seen is that we can start directly with an expression for phi of x in terms of creation and annihilation operators, including the corresponding plane waves, which I express them in terms of f of k. Same thing which also we can do with the pi of x essentially. Oh god, I put the dot on this, so okay, there is a typo here. So pi of x essentially is this, and then I argued that this is a multi-particle system, and to give you more uh, uh, clear picture, what I did was I essentially wrote down, I took a discrete case in the beginning. Essentially I just took an example for the discrete case essentially, where I make the k, the momentum, to be a discrete variable. Essentially we have k1, k2, k3, k4, and correspond to each k1, k2, k3, k4 I write a1, a2, a3, a4 and so on, a1 dagger, a2 dagger, a3 dagger and so on. So, and then I re-express my Hamiltonian. Here it comes out to be this particular fashion essentially, that it is a series of harmonic oscillators running from 1 to n essentially. So, with this thing I can just revise myself that the number operator is given by this particular thing, n is equal to a dagger a, and so for I is equal to 1 you have and the Hamiltonian to be written in terms of, oh, this is the Hamiltonian. The Hamiltonian is written in terms of n plus half is equal to omega. So, and each state is given in this particular fashion. The number operator acting on a state n gives you the number associated with that state, whereas a dagger acting on the state n gives you n plus 1 times n plus 1, essentially the state n plus 1. So, it changes the state n to n plus 1, and so whereas the lowering operator, the annihilation operator, reduces the state by 1 unit essentially, like in simple harmonic oscillator. And the important point is that the total energy of the system is given by n plus half omega, and there is a 0 point energy where n is equal to 0, the ground state energy is non-zero. So, there is a half omega which is associated with the ground state energy. So, this is all we known, but now what we did was we started doing it for n states, essentially discretized n states. And what is the ground state? Immediately we wrote the ground state to be as uh, a direct product of n ground states corresponding to each harmonic oscillator, and so it is 0 1 0 2 0 3 direct product 0 n, and so this gives me the picture that okay, this is a the states of this system are direct products of a bunch of harmonic oscillators. So there is a complicated Hilbert space which is direct product of the Hilbert spaces of n harmonic oscillators, n harmonic oscillators. So so what happens is uh, so and in this space the ground state is this particular thing. So the Hilbert space Hilbert spaces of n harmonic oscillators. So this is some different kind of Hilbert space essentially, okay, and the ground state of this Hilbert space is such that any of the A operators, any of the annihilation operators is vanished essentially acting on this ground state, uh, meaning vanishes the ground state essentially. So AI times 0 essentially is equal to 0 for any of AI essentially, whichever AI is it essentially. The nth state again is essentially a direct product of nth states of the n harmonic oscillators, and this you can re-express it in terms of a Dagger operators. And the funniest thing is that you have the ground state again has I and I1 is equal to n half omega I. So it is the ground state energy is non-zero essentially, it is non-zero, it is half omega I times n essentially omega I times meaning omega I time plus omega I plus omega I n times essentially it is a large energy for a ground state essentially. Now when this will create a problem when we do a particle interpretation of each of these states essentially of these Hilbert spaces, and this is now we will do that in this lecture essentially, yes. So again continuing. So what we have seen is that the ground state is a large energy essentially which is half omega I times roughly n times of this thing, assuming omega I is the same for all the roughly of the same order of magnitude for all the things. So it means that there is a significant ground state, and this will be a problem later on when we define the vacuum state for the entire thing essentially. So what we define. So before doing this further essentially we will just do the continuum state essentially, the continuum case essentially. So now let us take K to be a continuous thing, and we have already defined in terms of and defined the phi and K and its annihilation operators, and we have defined everything. Now let us look at what is the Hilbert space and the energy associated with this continuum case essentially. So first we have A of K is equal to 0 acting on the vacuum state, okay, is equal to 0 for all K. It does not matter, K is continuous essentially for a, okay. So then we can define something called an occupation number or the n number. So n oh, okay, occupation number n k is integral and n cap of k is equal to a dagger of k a of k. Okay, so um, for each uh, for each k mode essentially I define a number operator essentially which depends upon the k value, and then I can define an integral of all this number operators individual. It is like adding up all n of k and n1 of k, n2 of k in the discrete case. I can define essentially the n of k essentially n of k, and then I can define a total n. The total n is an integral instead of summing over all the n's. I define I assign some. Okay, so this is so so this is sometimes called occupation number density, and this is called occupation number. Okay. So the number density is defined between the volume k and k plus dk. Okay, we can take a small region k and k plus dk, and in this you can define what is our occupation number density n of k, because it is now continuous variable essentially n of k essentially, and then take all this occupation number density, integrate it over take the occupation number density and integrate it over k, and that gives you n essentially the total occupation number. So n of 0, so d cube of k a dagger of k a of k acting on 0 will always give you 0. So the occupation number of the vacuum state is 0, but as we will see that it has a large energy density essentially. Okay, this will create a problem. So the occupation number of the vacuum state is 0 essentially. So the vacuum state has 0 particles, or as we will see we will give the particle interpretation. Okay, occupation number is 0. Now the first excited state or the first state is essentially you can act a dagger of k acting on the vacuum. Okay, and this gives me some state essentially. Okay, is equal to sum 1, okay, a dagger of k now how do I show this? You can show this so this is so if I act a dagger of k acting with on vacuum, it produces the one eigenstate essentially the first number, okay, one state essentially. So how do I show it now? Okay, it is rather than that, okay, let me, it is better that I act n, okay, let me put an n on this, that is better actually. So it creates one state. So a dagger acting on 0 creates one state. How do I show this? I take n of a dagger acting on 0 is equal to d cube of q a dagger of q a of q a dagger of k acting on 0, and then I can express this. Okay, this is, you can I'll also give it as a homework, essentially a dagger of q, a of q, a dagger of q k essentially. So, this gives me a delta function plus a dagger of k, a of q all acting on 0. So, this gives me integral d cube of q, a dagger of q, a delta function, because we know this is a delta function, plus a dagger of k, a of q, k, then that thing, acting on 0. Okay. Now, this is what a dagger acting, there is some a missing essentially. So, some bracket, okay, uh, ah, okay, there is some bracket missing. Okay, I think then it's fine. I think okay, a dagger of q times a of delta of q, this is a of k, essentially this gives me a of k, and this gives me 0. So, this just gives me a dagger of k acting on 0. So, this is that it gives me one state. So, you are creating one state, the number, it is occupancy number is 1. So, its occupancy number of acting a dagger 1 is essentially this. So, if you have an occupancy number, okay, you can now prove the same thing for a large number of states essentially. So, if we have so n number of states acting on it. Now, this is what we have seen for the discrete case, but you can do it for the continuous case also. Okay. So, you can, the higher number of states, say for example, if you want to create Ni of k1 and 2 of k2, okay, Nl of k L, okay, no, that's fine essentially. So, this will be again acting a dagger of k1 n1 times root of n1 dagger. Okay. This is what we did for the discrete case. So, we want to do the same thing for the continuous case. How does it appear essentially? So, no, product discrete case. So, now what we do for the continuous case is that we do the same thing, n, some n states essentially are created with a momentum k1, another n2 states are created with a momentum k2, and so on. So, NL states are created with a momentum KL. Okay. So, this, each of them will be expanded in terms of some a dagger of k, a of k. Okay. This is for the number, okay, we should also write n of k. So, this is the n of k operator. Now, each n1 is acting times a dagger of k1 acting on n1 times root of n1 dagger, what do you call, factorial, and then you have A acting of with the K2 momenta n2 times root of n2 factorial, so on. So A acting L time A of KL acting NL times by root of NL factorial, all acting on the vacuum state. So you can evaluate this thing again and get the what is the number density operator for this particular state essentially, and this will end up being in the continuous case again sum over this will end up being something like I is equal to 1 to L Ni del cube K minus Ki, okay, Ni K1 and 2 K2, same state essentially the same state. So you end up having very similar to the case of the discrete case essentially, okay. So each N1 is essentially is the occupation number density coming from K1 plus K2 dk, okay, and so that how we can build up the occupation number, calculate the occupation number this particular case essentially, and then we can define N as usual the number of, so so the N is equal to again some more I1 to N L Ni. So instead of delta Ij you have delta Ki minus K bar minus Ki for each N, okay, for each N you end up having with this delta function, and so this gives me the numbers of this thing, and the total number density is given by this particular occupation number densities. Now how do you know that each of this state is actually a particle? How do you interpret this in particular state? Every excited state is a particle. So the interpretation is as follows essentially, that so each state is every excited state is given in this. The interpretation is that the Hamiltonian has a perfect thing is given in this particular fashion. So A dagger K A of K plus A of K A dagger of K, and the momentum is given in this particular fashion. So you know that the Hamiltonian acting on the vacuum is equal to vacuum energy density times E, and the momentum acting but the momentum operator, which is defined acting as d cube of K half K A dagger of K A of K plus A of K A dagger of K. Now this momentum operator acting on the vacuum is 0. You can calculate it actually, so you can show that this is nothing but 0 essentially acting on the vacuum. Okay, take the same analysis. This is okay. How do I know that? This is just d cube of K 1 by 2 K A dagger K A of K plus A of K A dagger of K, whole thing acting on the vacuum essentially. So this gives me A dagger of K acting on K, so that gives me d cube of k times half delta cube of 0, which is 0. Okay. So, we know that the momentum vacuum has energy. We will see how to E0 is the 0 point energy, which is large and everything, but it has no momentum. Okay. Okay. So, this it has no momenta, and so the vacuum cannot have any states, essentially it has 0 states essentially. Now, but consider the first state. So, let me call this state to be psi. This will be a dagger of P acting on 0. Now, I have shown that n of psi is equal to 1 of psi. This is already shown. So, its occupation number is 1. Now, what is h of psi? H psi is equal to integral d cube of k omega k this is the Hamiltonian, and what is psi? This is a of P acting on 0. So, this you can solve, this gives me omega p plus E0 psi. So, it picks up a frequency omega p. Okay. It has an energy which is omega p times psi, and E0 is nothing but the ground state energy. It's nothing but your ground state energy. So, what we are seeing is that the ground state of this huge Fock space, I did not use the word Fock space, I will use it in 1 second. The huge Hilbert space spanned by this direct products of n harmonic oscillators which are continuous, and so the ground state has 0 momenta, has non-zero energy which is E0, which we know that it is infinity, and the first exit is a very large quantity for the discrete case, and for the E0 for the continuous state is also almost 0 essentially. E0 is also very close to infinity. So, this is the energy, and the first excited state has a definite energy omega p, and it also has a definite momenta we use the same momenta formula now. Okay. Now, this will give me, once you solve this for this thing, essentially this gives me P, a dagger of P acting on 0, this is nothing but P of psi. Okay. So, this thing has a definite energy, definite momenta, independent, essentially it is an independent momenta. Okay. So, this means that this is like a particle. So, this has each excitation has a definite momenta definite energy with and mass, and so is a particle on its own right. So, at every excitation is like an individual particle essentially. So, every excitation is like an individual. You can have multiple excitations, that means you have a multiple particles essentially. You have multiple excitations, you have multiple. So, every excitation state is a particle and multiple example. So, this means you have multiple particles defined by this field essentially, and so the Hilbert space, this will be important to us essentially. I will come back to Hilbert spaces again. Corresponding to this has a special name, multiple particle system is called a Fock space. Okay, this sort of finishes our canonical quantization, but there are still some lingering problems. Like for example, the energy of the vacuum is infinite and so on. So, but we have essentially finished the process of quantization essentially. So, the process of quantization is essentially you start with this free scalar field. Okay, it took over for about 3 classes essentially, and then expand this phi and the conjugate momenta in terms of modes, harmonic oscillator modes, okay, various momentum modes, and then impose uh, the canonical quantization conditions, which end up being the quantization conditions on the harmonic oscillators, and then we describe them as we calculated the number densities, and we also calculated the energy operator, and then we showed that every excited state acts like a particle because it has its own momenta, it has its own energy. So, this is for the zero state essentially, or the vacuum state. Okay. So, what, and it has its own momenta and for a given mass essentially. So, if you have multiple excitations, you have multiple particles. So, at the end of the day, what we have developed is interpreted as classical field into a quantum picture in terms of multiple particles, okay, in terms of multiple particles essentially, and we call that particular space as to be a Fock space. But still, of course, there are some lingering problems which we will deal in the next class, essentially about, especially about the vacuum energy and other things. So, thank you very much, and I will see you again soon. Thank you.